As we started to think we were approaching the bottom, we did the very scientific salt test, which meant we were licking little bits of the offcuts to see how close to the bottom we were.
Doesn't sound very appealing as an ice lolly, salt-flavoured
No,
ice
it
lolly.
was pretty unpleasant.
How do scientists know that climate change is happening? Well, there's direct observational evidence, things like air temperatures increasing, sea levels rising, but those data only go back so far. And that's why scientists have to look at nature's record books to understand what our world was like thousands or even millions of years ago, from fossilised pollen and tree rings to ancient seashells and ice cores. These records, put together, show us what happened in the past, but they also feed into our climate models and help scientists predict the future. So this week on The Climate Question from the BBC World Service, we're going to be looking at one of those records, ice cores, and asking how do they show that our climate is changing? I'm your guide, Greer Jackson. In the studio, we have Dr. Liz Thomas, Head of Ice Core Research at the British Antarctic Survey in the UK. Hello.
Hello.
And down the line in the US, we have Lonnie Thompson, Distinguished University Professor of Earth Sciences at the Byrd Polar Research Centre at The Ohio State University. Hello, Lonnie.
Hello, good to see you.
So, when I was preparing for this programme, I kept thinking of ice cores as a giant ice lolly. Is that accurate?
Nearly right. So they're big cylinders of ice that we drill down through ice sheets or glaciers, but we try not to lick them. We tend to analyse them instead.
You wouldn't ever drink them once you've analysed them?
I have to say I have.
You have?
Yes.
Do they taste different?
Well, we had a recent project. So 2 seasons ago, I was drilling, actually, rather than through an ice sheet, we were drilling through an ice shelf. So this is where it, actually the floating tongues. And we started drilling and we didn't want to go too far because obviously we didn't want to drill all the way through the ice shelf. So as we started to think we were approaching the bottom, we did the very scientific salt test, which meant we were licking little bits of the offcuts to see how close to the bottom we were.
Doesn't sound very appealing as an ice lolly, salt-flavoured
No,
ice
it
lolly.
was pretty unpleasant.
Lonnie, have you ever tried an ice core before? Have you drunk it or licked it?
Oh, sure. Yeah, no, we've, if out in the field when you're drilling, you drill extra cores and, yeah, they're available for mixing and drinks and things like that. So, yeah, they're unusual. And if you get them deep enough, the air, the bubbles are under pressure, so they kind of pop and fizz when the ice is melting. So, yeah, the ice is remarkable in many ways.
Yeah, I bet. And speaking of ice lollies, didn't you have a run-in, Lonnie, with an ice cream truck in your early days of ice core collecting?
Yeah, we work in the low latitudes and in very warm parts of the world, and so we were moving ice from Gulia, our first expedition out there across the Gobi Desert, and the drive shaft fell off of the truck. But we were very close to Askew, and we went in. There was a little ice cream shop. We bought up all the ice cream, gave it to the children, and put our ice cores in there until they could fix the truck so we could continue our journey across the desert. So yeah, we've had some close calls in some of these remote parts of the world.
Yeah, I bet. And my producer also tells me there's a story to do with yaks and whistling.
Well, we've been very fortunate to be able to drill ice cores in 16 different countries.
Wow.
And every country is different as far as what's available for logistics. But if you're drilling in the Himalayas and you're drilling above 23,000 feet, it's very cold. It's very polar in that sense. And you can use Sherpas and porters to get the ice down to the margin of the glacier. But then you have to put the ice into insulated boxes, and you have to seal it, and you have to get it from the edge of the glacier down to the plateau where you can bring in a freezer truck. And that's still another 4,000 feet below. And so if you're in the Himalayas, the only animals available are yaks. And yaks are incredible creatures in that if you have a cat, their mentality is very much like a cat. They like to do it their way. And so we had to have special Tibetan whistlers to calm the yaks, but we could put 2 of our ice core boxes on a yak, and each box contains about 6 meters of ice. And we drill 500 to 600 meters of core, so you have to have a whole herd of these yaks. And so getting them down to the freezer truck, you have to have a lot of input from the local indigenous people who know how to handle them.
Wow, the
Once they get
sound
in,
must be incredible of all those people whistling to keep the yaks walking in line.
it's an amazing scene to see them stretched out in a line going down the side of the mountain. So it's a journey. It takes about a month to move the ice from these remote areas to get them back to the freezers here at Ohio State.
Gosh, what dedication. Liz, I imagine it must be similar with your cores where you're drilling in the Antarctic.
There's similarities, but I think
Not the yaks.
No, definitely not the yaks. I think we both work in very remote places, but most of my research has been in the polar regions. And we're particularly fortunate in the UK that we actually have a really expert logistics part of our organization. So actually some of the practical, bringing the cores back is probably easier in Antarctica, which sounds crazy being in the middle of Antarctica. And I'm just saying that the logistics is easy. But our cores, we tend to fly them out to our station where they'll go onto a freezer and then they're shipped all the way back to the UK. So it's a very long time. So we may not see the cores for actually maybe 6 months because it takes a long time to get back to the UK. But I don't have to integrate so closely with the local wildlife in order to get my cores back.
But the environment is still really extreme though, isn't it?
Yeah, so I think the similarities are we're both working quite often at altitude and it's really the temperatures. And for me, it's not that the temperatures can be pretty bad. It's the wind. That's the bit that I think really kind of wears you down. And for Antarctica, it's one of the windiest continents on Earth. And so when you've got constantly being battled with cold winds, it can be quite a challenge.
Well, considering neither of you look weather beaten at all, you have to tell me what your skincare secrets are. But given the challenges, Lonnie, perhaps you go first. Why do you do it? What is so exciting and interesting and important about these ice cores?
Well, I've been at this for about 50 years, and I still find ice cores amazing. I think they're probably our best recorder of the past on this planet, in that they record not just things like climate through isotopes or precipitation to annual layer thicknesses, but they also record the forcings of climate, the things that have caused the climate to change through time. Things like volcanic eruptions through tephra, sulfate layers. We have a history of output of the sun through cosmogenic nuclei, beryllium-10, chlorine-36. And then perhaps most important, it gets from the polar cores, we have this long history of greenhouse gases, carbon dioxide, methane, nitrous oxide, over the last 800,000 years, and soon it'll be much longer than that. But it gives us a perspective on the 21st century where we live. And that perspective, I think, is also a wake-up call for all of us of how rapidly our system is changing.
Liz, why do you do what you do?
I think that was a fantastic answer there. And I'm following someone who's been doing this for such a long time. I mean, very similar. I'm still really excited about the science. And particularly, projects that we're working on now where you get that first glimpse of maybe a key period in our climate history and you're the first ones to start to obtain data to sort of piece together what was happening. But I'm also on the adventure side. So I do love the field work. So I'm working in the lab at the moment, but the field work is also a real a bonus for me, and getting to go places where no one else has ever been. Quite often, that no one else will ever go there again. And it's that kind of feeling completely isolated or being somewhere, incredibly remote. I think you can't really, it's a sort of buzz that keeps you going.
So let's talk about some of the things Lonnie just mentioned. I'm really excited about the bubbles. Tell me about the bubbles.
So the bubbles are fantastic. So as snow falls on an ice sheet, it becomes compressed into layers. And as it does so, it really traps the air from the time when the snow fell. And as it becomes more compressed as you go deeper down, then these become trapped into tiny bubbles. And effectively, what you do when you then release those bubbles back out into the atmosphere is you're able to look at what the composition of the atmosphere was at the time. And there's some really important indicators there. So, as Lonnie was just mentioning, the greenhouse gases, carbon dioxide and methane. And being able to track those back through time is such a powerful message for the whole sort of climate story and for policymakers to be able to really see how carbon dioxide has changed over, at the moment, the past 800,000 years. And as Lonnie just alluded to, hopefully we're going to extend that even further. But being able to show how this is part of natural climate variability right up until the point of the Industrial Revolution, where we start to see a really dramatic increase and acceleration in greenhouse gases. And I think it's so powerful to just show people ice and allow them to hear those bubbles, because if you hold it to your ear, it fizzes and pops and crackles. And being able to see that we're not manipulating this data in any way, it's not a proxy, it's not telling you about something else. It really just is extracting that bubble of air and capturing a record of what the climate and what the atmosphere was like.
So it's a key piece of evidence of the climate change puzzle. And Lonnie, you mentioned that it wasn't actually just climate change and the planet warming gases. You mentioned there were lots of other things that we could draw out from ice cores. And I think your work also works on viruses and bacteria.
This is the beauty of the ice, is it records whatever's in the atmosphere. And as our technology improves, we can extract other things from the ice. And in the low latitudes, we've been looking at the microbes, bacteria and viruses. And there's some really basic questions. This is a very important part of our system, but we know so little about it. But particularly, how do viruses and bacteria react to warmer climates and colder climates? How will they react to a warmer world in the future? But we also have histories of things like black carbon that we can measure that can tell us the history of fires. And we're working on a record right now from Huascarán, the highest tropical mountain on Earth, that goes back 30,000 years, and it's right above the Amazon basin. And we're hoping to be able to extend our understanding of what the natural fire history was before humans started playing a role. So they're a wonderful archive in time of anything that's in the atmosphere.
Why do you think they're better than other proxies? As paleoclimatologists, you often look at things like, fossilized pollen or tree rings or ancient seashells. Why are ice cores, in your words, I think the best, did you say the best type of data to our past?
My biggest response to that would be they're not living. Living things can adapt to their environment, and they can change. Whereas the ice, it's a physical property that's deposited on the Earth. Now, this is not to say that we don't have wonderful paleoclimate records from marine cores and sediment cores and corals and trees. And we need all of that to put together the picture of climate on this planet. But ice is special. And it's special because in today's world, we are losing it. And we're going to lose those archives of our past, or they're going to be compromised by melting that's taking place. So they are a fragile part of our environment.
And the black carbon, Lonnie, that you were mentioning before is just soot, isn't it? But Liz, what I want to know is, what does all this tell us about the future?
Well, some of the things that we're really interested in are actually understanding the whole climate system, and importantly, some of the processes that are driving change. So obviously, as humans on this planet right now, we're interested in what's going to happen in the future. But we know that the sort of current rise in greenhouse gases is related to human activity. But it's not just that that's going to govern how the climate will change. It's also that underlying natural changes and those natural processes, these feedbacks in the climate system. And so it's really important that we get a really good handle on that. And an example is, carbon dioxide is such an important part of our climate, but actually the Southern Ocean plays a really key role in potentially, at the moment, we're drawing down atmospheric CO2 into the ocean and locking it away. But we also know that at times when there's been strong winds, for example, or when the sea ice has retreated, the ocean can actually act as a source. And so it can release this carbon dioxide that's been locked away in the deep ocean. And so it's really vital that we understand what's driving those processes. How are winds and atmospheric circulation playing a role? What's the impact of changing sea ice, whether we've got a lot of sea ice cover in the Southern Ocean or the Arctic or not? So it's really getting to grips with all of these processes, because that's only then can we start to build together this picture of how the climate is potentially going to behave.
Right, and this data is really important, Lonnie, because it then goes into things like our climate models, which sort of predict what happens in the future. And, often when you look at those graphs, it gives you sort of like an error bar, right? It could be this and this, and this is the average. But actually, the more data we have about the past, then surely those error bars narrow, right?
Yeah. We have to understand both the natural forcings in our climate system, as well as the anthropogenic impacts that we're now having on the system. And you really need these archives of the past in order to do that.
Now, Liz, I want to ask you about this very exciting ice core that you have got your hands on recently from the Antarctic.
Yes.
Why is it so special?
At the moment, we're really fortunate. We are currently, or the team in the lab now, are currently analysing what we believe is the oldest continuous ice core record ever. And this is part of the Beyond Epica Oldest Ice project. And this was a major international consortium EU-funded project. And what we are doing, so thanks to UK funding, we're responsible for analysing this ice and extracting this really important climate information. And what we've been able to do is extend our understanding of the natural processes, these natural glacial cycles. So this is as we've moved from relatively warm conditions, such as we're in today, interglacials, to these extreme cold conditions, the glacials. And these are natural cycles. And what we're able to do is we've extended that record from 800,000 years, the previous oldest, and we've carried it on further back in time. And this is where I get a little nervous, because
How far, Liz? That's what I want to know.
I would love to be able to give a definitive answer, but we are currently melting. So what we can say is that beyond the point where we think we were at about 800,000 years, we've actually analysed another 100 metres worth of ice, and we've got some fantastic data coming out, which is clearly showing these cycles. So we're quite confident that we are still capturing this climate information. And our best guess at the moment, based on comparing it with a range of different archives that are already available, is we hope we've got to about 1.5 million years.
Wow. So that's more than double. No, just under double.
Yeah, nearly twice of the record that we've had before. And the reason why this is so important is because this captures a really interesting and still very intriguing period in our climate history. So this period beyond about 1 million years, we think that actually these cycles, these glacial cycles from warm to cold, they fundamentally shifted and changed. So what we are more familiar with in the recent Epica Dome Sea record is these glacial cycles lasting about 100,000 years. But there's evidence to suggest from marine records, for example, that actually prior to 1 million years ago, these cycles were much, much shorter. So they were taking place in the order of every 40,000 years. And because they were taking place much more rapidly, they weren't as extreme. So it wasn't getting as warm and it wasn't getting as cold. And the theory being that that meant that we couldn't possibly have had such large ice sheets, particularly over the Northern Hemisphere, as we've had in more recent millennia. And so this is a really potentially intriguing sort of analogue for maybe where we're heading in the future, where we've got smaller ice sheets, smaller ice caps, higher sea levels. And there's a lot of debate still in the community, but potentially the greenhouse gases were also higher during this time. So this is a good potential analogue for where we might be heading in the future.
Do you think we'll ever be able to go back further, Lonnie, than 1.5 million years?
Well, it's an interesting question. There's a lot of international activity right now trying to get the oldest ice on the planet, and most people believe it's in Antarctica. So there are over 400 lakes below East Antarctica, and there's rivers, and that means time is being removed from the base of those glaciers. So I would argue that you might find a mountaintop in far western China where it is so high and so cold and not so deep, so that you don't have geothermal heat coming up and attributing to melting, that you may have a very, very old record there. But unraveling that record because of the compression is a real challenge. So certainly the big effort right now is to find that oldest ice in Antarctica. But there may be surprises. This is the beauty of science. We don't know until we actually do it.
These glaciers, especially, at lower latitudes, some of the ones you've been working on, Ollie, they are at risk because of increasing temperatures, because of climate change.
Yeah, we have 4 cores in our archive that come from glaciers that no longer exist out in the real world. And unfortunately, about 8 of those glaciers that we've drilled and have records from now, those glaciers have a water table in them, which means it's melting at the surface, water's moving through the porous firn upper layers and erasing and compromising the climate record that has been preserved in those ice cores. And so I think one of the things that we have to think about in the future is how do we preserve the cores we already have? Because all of these areas, and eventually even the polar regions, those records are going to get compromised by a warming planet. And so how do we preserve the ice from the past? Because I know 20 years from now, there'll be more technology, there'll be things that can be extracted from these cores that we haven't even thought of. But you have to have an uncompromised ice core to make some of those measurements. And so preserving that ice for the future, to me, is a big concern.
I mean, all very, very good points there. And I think, again, it kind of comes back to, going out and trying to preserve some of these locations where they're at risk, but also the need to have these global records, because some of the drivers of, what's causing those glaciers in the mid-latitudes to be retreating and to be melting, are actually part of a big global system. So actually that's where the polar records as well can kind of add additional information. And as is touched upon, the polar regions are no longer this sort of safe haven where the records are not being disturbed. So a lot of the places where I have been particularly working, we are seeing melt layers even in Antarctic ice cores. And I've been fortunate to work in some of the subantarctic islands, and they're also very much at risk of melting because the temperatures have just been increasing so rapidly in the last sort of 20 years.
Lonnie Thompson and Liz Thomas, thank you so much for joining us on The Climate Question.
Thank you.
Thank you very much. It's a pleasure.
And thank you for watching. Don't forget to subscribe to the BBC World Service YouTube channel so you don't miss out. And if you have a climate question of your own, then please do write it in the comments below and we'll try and answer it in a future show. I'm your guide, Greer Jackson, and I'll see you next time.